Okay, so here's what we're trying to figure out now. We've got um, certain variables depend on certain other variables, and certain other variables depend on those variables, etc. Um, so let's try to get organized. What's a function of what? So um, I claim that our diagram is going to look kind of like this. U, V, and W give you X, Y, and Z. The name of this function is called f. And then as a function of x, y, and z, that function being called g, we can determine r, s, and t. So this is the sort of the flow of variables here. Right? Everybody okay? And we've got a couple of Jacobian matrices given to us. Now, note I just gave these Jacobians as just matrices at particular points, and so which numbers or which partial derivatives isn't really given, right? So let's write down now in what would be the natural way to compose these things. Well, I could write down the Jacobian of G compose F is Jacobian G times the Jacobian of F. Awkwardly, note here G was on the right, here G is on the left. It's awkward. It's just the nature of the beast. It's the way these things flow, right? So in the diagram, what's on the right, algebraically, it's on the left. Okay. All right, so now let's expand these out. These two matrices are just flat given. Let's just recopy them, but careful. The one on the left is the Jacobian of G, which I was being kind of a jerk here. I wrote that down on the right-hand side, right? And I want to make sure everyone's paying attention, right? Okay, so this matrix here goes on the left over here because it's Jacobian of G. It's the one that acts second. Therefore, it's on the left here in the algebra. So I have, all I know is I have a 1 and a 0 there. 4, -2, 2, and 1, 0. And then likewise, this is the Jacobian of F. That's the matrix that's up there on the left. So 1, 0, 3, 2, 4, unknown, and then -1, a couple of unknowns there. So this is all I really know. Okay, so step 1, or problem 1 down here. Can I compute the partial of S with respect to U? All right, I want to compute the partial of that with respect to that. Now, that's going to be an element in this Jacobian matrix because it's a partial derivative in the composition. And it's a partial with respect to the first input variable, so it's going to be in the first column here. And it's the partial of that second variable, so it's going to be this second entry. So that's what I'm trying to compute, right? Trying to compute that element of this product Jacobian. So the way I compute that, well, let's see here. That would be this row dot that column, and sure, I can compute that. 4 times 1, -2 times 2, 2 times -1. I believe that adds up to -2, if I did the arithmetic right. Yeah. So the point is this element, it's just, that row, that column, dot product, added up. Is that all right? Yeah. Okay. All right, now the next partial of R with respect to U. Well, that would be this element here. Let me, it's that element, partial of R with respect to U. First input variable, first column. First output variable means first element in that first column. So that's this guy. And that would be a dot product of this. Uh-oh, I don't know that number. But it's a product of that and that. And tragically, I just can't, if I don't know what that number is, I don't know what I'm multiplying by 1 to add up with this other stuff. So the second one, partial of R with respect to U, I just can't compute. Okay. Now the third one, if I remember correctly, is a little tricky. Same process, partial of R with respect to V, that with respect to that, second column, first entry. Trying to compute that element. So it's going to be this row dot that column. Now there's a couple of unknowns, but check this out. The thing that I don't know here, I'm multiplying it by 0, so the fact that I don't know doesn't matter, right? 1 times 4, cool, and then 0 times I don't know, again, doesn't matter. So even though there are these sort of missing elements, you can actually compute the partial of R with respect to V, that entry. Yeah. That make sense?
Yeah, I guess the only thing I was really confused about, like in the notation, like
Yeah.
you not, like I guess the point you not or something.
Oh, that's yeah.
So
Oh,
I didn't know
whoa.
what that's
Yeah.
like.
Okay. So right. So what we've got here, I mean, so there's a particular point U naught. It's a U naught V naught W naught. That's a point in this R3 here. That's a particular point. And now note in the statement of the problem, f of U naught is equal to X naught. So that point goes to that point. And the Jacobians were given at those points. So the Jacobian of f, the Jacobian of this guy was given at that point. And the Jacobian of g is given at x naught. That's that point.
So that's
And
how, okay, that's how you do the order of the composition, right?
well, no, it's how you know that these Jacobians actually relate to each other. In other words, where you evaluate when you multiply two Jacobians to get a composition Jacobian, this one has to be evaluated at the point which is f of where this Jacobian is evaluated. Right? In other words, if you go back to this picture here, in this picture, the Jacobian of g has to be evaluated at that point, which is f of a, namely this point. Right? Because the reason why is because if you've got a point there that's your sort of starting point in your first domain, that point has its image, and when this is moving with that velocity, that's what's making this move with that velocity, and that velocity of this point is what's causing that to move with that velocity. So since this is what comes out of the first function, this also has to be what's going into the second function, because we're composing them. So this Jacobian has to be evaluated at the same point that's the image of that point. Yeah, right, exactly. It's like in the single variable, excuse me, where's my, here it is. When you're talking about the single variable chain rule, G prime has to be evaluated at f of A if f prime is evaluated at A. So that has to be f of that for the chain rule to really make any sense. Yeah, that's all that is. Yeah. Okay. Okay, so that's the rest of that problem. Does that make sense to everybody? Any questions? Everybody happy? Okay.